In this mini lecture, I'm going to talk about the concept of work in a physics sense. To start with, I'm going to talk a little bit about springs. So a spring has a natural length if no force is being applied to it. If a spring is just sort of laying there or sitting there, it has a natural length it just wants to be at. We can pull the spring and make it longer, or push the spring and compress it. And when we do that, we change its length from its natural length to some other length. And the force required to stretch a spring, if you've ever done that, of course, as you pull the spring, the farther you pull the spring, the harder it gets to stretch it. This is expressed in this language as Hooke's law. So the force required to stretch or compress a spring a distance x from its natural length is directly proportional to the value of x. So we can write that F equals k times x. This value k is called the spring constant. The value of k depends on the particular spring that's being used. It reflects the strength of the spring. It might be the way it's manufactured, the material it's made of, whatever. Some springs are harder to pull than others. And this spring constant sort of captures that information about the spring. This spring constant, though, is constant for a given spring. So if you have a particular spring, the spring constant doesn't change for that spring. It always stays the same. So what am I really talking about here? What does this look like? Well, maybe we have, it's not looking much like a spring. Okay. So we have this spring here, and then, we stretch it out. And what we've got, this amount here, is the natural length. Right? That's the natural length of the spring. This amount here is going to be x. That's the amount that the spring has been stretched from its natural length. So let's imagine that I've got a spring balance. It's weighing, a weight of the force actually, and it's 5 inches long when there's no weight on the balance, and 8.5 inches long with 14 pounds hung from the balance. We can use this to calculate the spring constant k. Right, so we've got a spring balance. That spring is here, and if I'm holding this 14 pounds, with that 14-pound weight on it, that gives it a length of 8.5 inches. That's how long the spring is if that weight is on it. Of course, the idea is the natural length of this spring would be 5.0 inches. And so the distance is the amount that it's been stretched. I obviously didn't draw this to scale very well. So how do we calculate that spring constant then? Well, we could do it two different ways. It depends what units I eventually want to end up with. We're going to talk about work on the next page. When we do work in the U.S. system, when we're talking about stuff like inches or feet or pounds, we would either get the most common unit of work in the English system is foot pounds. In the U.S. system, foot pounds. But we could also compute inch pounds. It depends how we measure distance. And so we could do this problem two ways, depending on whether you want your final answer when we do a work problem with this to be in inch pounds or foot pounds. So if I measure in inches, then we know F from Hooke's law, F is k times x. My F here is 14 pounds, and we're saying x is 3.5. So I would just divide both sides by 3.5. And if we do that, we get that k is equal to 4. And that's if we're measuring x in inches. Now, I can also look at feet. It's still k times x. Oops. F is still 14 pounds, but now I'm going to say it's 3.5 inches, but out of 12 inches, right? So 3.5 out of 12 if I'm going to be converting to feet. And if I look at that, then I could, I don't know, I hate decimals and fractions. I could multiply top and bottom by 2. That would be 7 over 24. And so then I'd multiply by the reciprocal. I'd get 24 over 7 times 14 would be k. 7 goes into 14 twice. So I would get k is 48. And that is if x is being measured in feet. Okay, so we can calculate that value of the spring constant, and now I know how that spring is going to behave, because now I can rewrite my Hooke's law equation, F equals kx, but I'll either plug in k equals 4 or k equals 48, depending on what units I want to end up with. In physics now, the concept of work is defined as force being applied over a distance. Now, if the amount of force is constant, it's really easy to calculate work. We just multiply force by the distance over which it's applied. So, really easy example, if I have a box and it weighs 10 pounds, and I lift that box 3 feet, then my work is just 10 pounds times 3 feet, which would be 30 foot-pounds of work. Right? That's really easy. So if I lift 10 pounds up 3 feet, that's 30 foot-pounds of work. Okay. Now in the metric system, force is measured in something called newtons. Well, in the US system, force is measured in pounds. So we've got that here. The weight of the box is really the force that the box is experiencing due to the force of gravity on the Earth here. In the metric system, remember, mass is measured in kilograms, and that's not a force. To convert to newtons, to get a force, you would need to multiply the mass by the acceleration due to gravity, which on the surface of the Earth is 9.8 meters per second squared. So that the number of newtons is the mass, the number of kilograms, times this 9.8 meters per second squared. This is a result of Newton's law that says force equals mass times acceleration. So force, newtons, is mass, kilograms, times this acceleration, 9.8 meters per second squared. So here, if I have a box that weighs 10 pounds, that's already a force. If we said that this box had a mass of 10 kilograms, I couldn't just take 10 times 3. I'd first have to take 10 times 9.8 and then multiply by 3 to get my answer in newtons. Now, that's the idea if I just have a box that's the same weight. It's more complicated to calculate the work done if the amount of force that's being applied changes. Well, with the box, for instance, what if as I'm lifting that box, maybe it's a box full of sand, maybe some of that sand is leaking out as I lift the box, so that the weight of the box is changing as I'm lifting it. Or, for example, as you stretch a spring, the amount of force needed increases as the spring is stretched farther. So, if you stretch a spring 6 inches past its natural length, you cannot just multiply a single force by that distance of 6 inches to get the work, because the force changes over that distance. When you pull at the first inch, that's going to take less force than when you pull at the last inch, because you've already stretched it. So what we do, we imagine dividing the 6 inches that we're going to stretch the spring into many smaller distances. Then we approximate the work needed to stretch the spring over each of these smaller distances and add them together. Sound familiar? Well, yeah, this is a Riemann sum. So I've got a force evaluated at a particular representative x-coordinate, and then I multiply by the distance, delta x, that I'm applying that force over. The idea is really here, I have this total distance, I'm wanting to apply that force from x equals a to x equals b. And what happens is I take a tiny little distance here, and inside there I take a value x sub I star, that's a representative value there, and I take delta x. So I say, okay, on this little subinterval, I need to get a force. I'll take just one of the forces. I know the force is actually changing even over this little subinterval, but I'm just going to take a force somewhere in that subinterval. So I'll evaluate that force at this representative x coordinate. That gives me a force I'll assume is constant over the whole subinterval. I know it's not, but we'll take care of that in a second. So that's the force over this subinterval. How far am I applying this force? Well, it's over this distance delta x. So that's the amount of work that I do on this little subinterval. But then I add that over n subintervals. I divide this whole distance into a bunch of these little subintervals. What I do though then, I take the limit as n goes to infinity. As I do that, delta x goes to 0, and my force gets so that it doesn't really change over the interval because I'm essentially evaluating the force at every single x coordinate along this interval. And of course, once I do that, it's just the integral then from a to b of this force function dx. So this goes back to what we did a little bit earlier here. The spring of a spring balance is 5 inches long when there's no weight on the balance, and it's 8.5 inches long with 14 pounds hung from the balance. How much work is done in stretching it from 5 inches to a length of 14.5 inches? Okay, so we didn't do that second part, but we looked at the first part, and we used that to do the spring constant, back earlier. So if I want to measure x in inches, remember we already found if I do that, that k was equal to 4. However, if I want to do x in feet, we found that k was 48. Right? That's what we found a couple pages back. So I know my force function from Hooke's law, F is equal to k times x. So that would be F is equal to 4 times x. And again, this is my spring. So that's 5 inches. We're saying this is being stretched out a total of 14.5 inches. So that, of course, means it's being stretched 9.5 inches. I'm going to start here. X is going to be 0, and I'm going to end up here where x is 9.5. Right? And this, of course, is all inches. So when I set up the integral here, it's going to be the integral from a to b of this force function f of x times dx. Well, as I'm integrating here, as this spring is stretching down, it's starting at x equals 0 at that natural length of 5, and it ends up here at 9.5. And if I'm measuring in inches, my force function is this 4x dx. If I take the antiderivative, 4x squared over 2, evaluated from 0 to 9.5. So that's going to be just 2x squared, evaluated from 0 to 9.5. So that's going to be 2 times 9.5 squared minus 0 squared. And if I do that whole work, that's 180.5, and those units would be inch pounds. Okay. That's a sort of strange unit of work. If you're fine with that, that would be cool. If you want to do this and end up with foot pounds instead, well, what's going to happen, I'm still going to get this same basic integral, but now my limits of integration have to be in regards to feet instead of inches. So 0 inches is still 0 feet, but this here is going to be 9.5 over 12 is going to be my upper limit in this sort of case. And my force now function is 48 x dx, right? So my F is still kx. So F is 48x. That's where that came from. And I don't like 9.5 over 12. I'm going to multiply top and bottom by 2. That's going to give me 19 over 24. So I would get 48x squared over 2, evaluated from 0 to 19 over 24. So that's going to be 24x squared, evaluated from 0 to 24ths. So I'm going to get 19/24 squared minus 0 squared. So that's going to be 24 times 19/24 times 19/24. Two of those cancel. And so I get 361 over 24, and that would be foot-pounds. Now, it's really not that big of a deal then when we think about this. If I take this 180.5 and I multiply top and bottom by 2, I end up getting 361 over 2, those inch pounds. And then, of course, how do I convert inches to feet? I have to divide by 12. So if I divide by 12, that's putting another 12 in the bottom, and I get from that 361 over 2 to 361 over 24. So it's really not that hard to convert from inch pounds to foot pounds, but we see that it works out either way here if I do the problem like that. So that's one type of problem, work problem that we can solve with an integral. We can do stuff with springs. Here's another situation. So a cable that weighs 3 pounds per foot is used to lift 500 pounds of coal up a mine shaft that's 800 feet deep. Find the work that's done. Now, we're going to sort of break this into parts here. So let's show first how we approximate this required work by a Riemann sum. And what's going to help is we're going to let x be the distance in feet below the top of the shaft. So I've got this mine shaft. My amazing art ability here. Okay, so we have this mine shaft, and somehow then we've got a cable. So this is my cable, and it's hauling up coal somehow, and this coal we know weighs 500 pounds. And I've got this distance from the top of the mine shaft to where the coal is. I'm going to call that x sub I star. Right? That's a little distance. And then what I've got here somewhere, I'm going to move that coal up a distance delta x. So the x sub I star is how far down the shaft I am. I need to know what f of x sub I star is. So if I'm lifting up that coal a little distance there, right? So it's down here. I've already lifted it off the bottom a little bit. I'm moving it just up another inch or so, let's say. How much force is it going to take to lift that up another inch? Well, I've got to move the whole 500 pounds of coal. That's a given. But the cable weighs 3 pounds per foot, so that's not, that's not insignificant. 800 feet deep, 3 pounds per foot, that would be 2,400 pounds of cable at the beginning that has to be lifted up. So this force function has two components. We need the weight of the cable plus the weight of the coal. Now the weight of the coal doesn't change. That's always the same, but the weight of the cable does change here. How much is the cable? 3 pounds per foot. So 3 pounds per foot. And then we need to know how many feet. And then the weight of the coal is just the 500. Well, how many feet? That's what we could use this x sub I star then. That's how far down the shaft we are, right? Eventually we want x sub I to be 0, x sub I star to be 0. That'll be up here when the coal's at the top of the shaft. At the beginning, I didn't label that here. At the beginning, I've got, of course, a total distance of 800 feet. Okay, so at the very beginning, when the coal is at the bottom of the shaft, x sub I is 800. At the very end, it would be 0. Okay, so what do I have here? Well, this is just going to be then 3 times x sub I star. That's the length of the cable, plus 500. And that's what we get down here then. That's the Riemann sum that would find this work. What would it be as an integral then? Well, it's going to be the integral of this 3x plus 500 dx. And what is x going to be? Well, we usually go from lower to higher. The smallest x is going to be is 0. X is going to go from 0 all the way down to the bottom of the shaft, which is 800. And then how do I evaluate that? Not too bad, right? We would get 3x squared over 2, take the antiderivative, plus 500x, and that's going to be evaluated from 0 to 800. So that's going to be 3 times 800 squared over 2, plus 500 times 800, minus then I'm going to get 0 plus 0. Right? When I plug 0 in for x, nothing much happens. And if we do that on a calculator, we get 1,360,000. What were my units? Well, 0 to 800, that was feet, and it was pounds, so this would be foot-pounds of work. Okay, one more example. A swimming pool has a rectangular base 11 feet long and 22 feet wide. The sides are 4 foot high, and the pool is half full of water. How much work will it take to empty the pool by pumping the water out over the top of the pool? Assume that the water weighs 62.4 pounds per cubic foot. Give your answer to the nearest foot-pound. That is the weight of water, just rounded to 1 decimal point there. So we've got this swimming pool. How is this going to lead to an integral? We've got this swimming pool. It's rectangular, right? So it looks roughly like this. And it's 11 feet long and 22 feet wide, or however, it doesn't really matter, right? So we can say this is 11, this is 22, and it says it's 4 feet high, but it's only half full of water. Right? So there's only 2 feet of water actually in the pool. So how much work will it take to empty the pool by pumping the water out over the top? Well, you know, we could calculate the total weight of the water that's in the pool. We could find the volume of the water in cubic feet, and you know, the weight then is just going to be 62.4 pounds per cubic foot times the volume, because the volume will be in cubic feet, and then the cubic feet will cancel and I'll be left with pounds. So we could calculate the total weight of this water, and then you'd say, oh, well then I just need to move all that water 2 feet. No, see, that's not really it. The water at the bottom of the pool has to go up 4 feet. The water at the at the top of the water level, that water has to get moved 2 feet. But some of the water gets moved farther than other water. And so the amount of work that's done is going to be different, not because the weight is necessarily changing, but because the distance is changing for each part, each little piece of water. So how do we approach this? Well, we think of, sort of imagine we could freeze the water, although that would change the density, so we don't really want to do that. But assume we could freeze the water, and then we're just going to take a thin slice of the water. So imagine just coming here and just taking a thin slice of that water all the way along, and we're going to call that thickness delta x. So what does that look like? It's sort of hard to see it there. So right now that's still 11 and that's still 22. So now what's the volume of this slice of water? Well, it's 22 feet by 11 feet. Probably not using x there. Times 11 feet times delta x feet. And if I multiply that, 11 times 22 gives me 242 delta x cubic feet. So what's the weight, which is really then the force needed to move this slice? Well, that's going to be 242 delta x cubic feet times the 62.4 pounds per cubic feet, which then when I multiply the 242 times the 62.4, I get 15,100.8, and then delta x, don't forget, pounds. And now what's the work going to be? Work is force times distance. So the force is this 15,100.8 delta x. But now, what's the distance I'm lifting that slice of water? Well, the distance I'm going to lift that slice of water has to be from the top of the pool down to where this slice is. And of course, that value is changing. At the bottom of the pool, if the slice is on the bottom, all that water has to get moved up 4 feet. At the top of the water level, that only has to go up 2 feet. But I'm going to let this be essentially a little x sub I star. Okay? And so that's this work that's done. It's this force times the distance, which is going to be x sub I star. So I'm going to add that all up. I'm going to let the number of subintervals go to infinity so that the width goes to 0. Add them up. That's going to give me a definite integral. So my total work, give me the integral. We've got 15,100.8. I've got an x, and I've got my dx. Right, the x sub I just becomes x, the delta x becomes dx. And what are my limits of integration? How far does x have to go? Well, when I'm at the bottom of the pool, x is 4, right? The water at the bottom of the pool has to go up 4. When I'm here at the top of the water level, that's going to be when x is 2. So my x has to go from 2 to 4. So when I take the antiderivative, I increase my exponent by 1. So I put in, I can factor out the 15,100.8 over 2. then I'm going to get 4 squared minus 2 squared. So that's 15,100.8 over 2. 16 minus 4 is 12. So that's going to be 15,100.8 times 6, which is, I can't read my writing, I think, yeah, 19,604, 90,604.8. And what are my units? X here is measured in feet, and I was measuring the weight in pounds, so that will be foot-pounds. Now, these examples, we've just sort of scratched the surface of these kinds of work problems that we can do. I just wanted you to have sort of a flavor for how that works. Obviously, where this would come into play then is, to do this many foot-pounds of work, if you have a pump that's rated at a certain amount of foot-pounds per minute or whatever, you would know then how long that pump would take to empty the water out of the pool. So engineers definitely would need to calculate this kind of stuff to be able to figure out how powerful of a pump do we need so that this can happen in a certain period of time.